Hello, welcome everyone. My name is Dhimandev Goswami, and this is my channel, The Common Math. And see, I've been talking about Pythagoras of late, and since we don't thank him enough for his contributions, and yes, it's not like I'm being very biased. I'm just making some conceptions in uh, how we are approaching in our modern mathematics. So yeah, so let's also go another piece of information, which was again stumbled upon by Pythagoras, and that was, you know, irrational numbers. So he was mostly working in geometry. So what he observed is that and when he took a square, and he saw that he was unable to, express the side. Let's say this is the side and this is the diagonal. So the ratio of this side to the diagonal as a ratio of two integers. So he was unable to, express that a by d in p by q form. So it is just another case. If you have not watched my previous video, you can just click the links above. Uh, it might not be timed pretty well. It might not be what I'm saying. It might not be timed well, but yes, you can go back on the suggestions and please watch the video where I talked about how there doesn't exist two whole numbers, or we can say two integers, which can be, a square of one can be expressed as twice the square of the other. So it's the same situation, and this situation actually led Pythagoras to, you know, talking about irrational numbers, because like the diagonals. So if we take a whole number, so let's say this is a and a, so the diagonal is always never, you cannot actually calculate it to in just a few steps, because the decimal expansion doesn't terminate. So, and since it never terminates and it cannot be expressed in the p by q form, so at the end of the day, we have irrational numbers. We call them, non-terminating, 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 and non-recurring. So non-recurring is like non-repeating. So non-recurring decimal expansion. So you cannot have uh, an exact value of a diagonal actually. So that was the pretty great problem. So this was the main things uh, that Pythagoras tried to imply. So uh, that we can easily construct the diagonal geometrically, right? Isn't it? We can easily construct a diagonal geometrically, but we cannot measure it in any finite number of steps. So this is the impossibility that sharply and clearly brought irrational numbers, right? Which I was already talking about, and the infinite processes which they seem to imply to the attention of mathematicians. So thus the square root of, like, say for example, if we take this side as 1, a equals to 1. So uh, later on, we can say that that square root of 2 can be calculated to any required finite number of decimal places by the process that we have been taught in school, that you just keep on dividing and dividing, and then like if it's satisfactory enough for you to just keep it in within two decimal places, then that's enough. But otherwise, you just cannot uh, get the exact value of such numbers. So this was the main issue that was pretty first brought by Pythagoras. So hope it was interesting, fact enough, and thank you so much for watching.